we have Juan Otazú. His talk is, he's from LNCC. His talk is Pricing Path-Dependent Derivative Securities, a New Approach.
Okay.
Okay, Juan.
Thank you. How is functional? Okay. Okay. Well, my talk is about pricing path-dependent derivatives and securities, a new approach. I'm Juan Otazú, and Jack is my advisor in the LNCC, and Jose is my co-advisor. So, in this talk we have these sections. One introduction, and in section 2 I talk about the discretization method. In the next sections I apply these methods for pricing derivatives and stock markets in interest rate derivatives. And after that we have numerical results. Okay, the history proper of mathematical finance starts in 1973 when Black and Scholes published their Hola, hola. Hola, ¿estás? Ah, okay. So, the history proper of mathematical finance starts in 1973 when Black and Scholes published their famous paper on option pricing. Then Harrison and Krebs in 1979 and Harrison and Pliska in 1981 made the link with the martingale theory. After that, we know that the price of asset is given by the risk neutral formula. Products available in the market can be very complex with diversity of exotic payoffs. And in special cases, it's possible to find a closed formula for its price. In more general setup, derivative prices must rely on numerical methods to solve the risk-neutral equation. For that, at least we have three methods: Fourier transform, Monte Carlo simulations, and PDEs via Feynman-Kac formula. About our method, we provide a new method for pricing path-dependent derivatives. It consists in a double discretization procedure, and the Feynman-Kac formula is used to find elementary conditional probabilities in not prices. So the use we make of the Feynman-Kac formula is very different from that of the standard methods. A consequence of our different approach is that our method admits parallel computing. The method works with arbitrary payoffs. It accepts continuous time as well as discrete monitoring path-dependent payoffs, and any diffusion consistent to the Feynman-Kac formula. In simulations with Basichek model, the method presented good performance in the full range of the initial conditions for the interest rate and did not exhibit instability in low volatility. So, the discretization method. Consider a probability space equipped with a filtration and the stochastic differential equation given by the question 1. And by a time and value discretization of the stochastic process X, we address the problem of solving this expectation, where B bar depends on the world trajectory of the X, the discretization of X. Let epsilon a positive constant and define the epsilon index discrete state space D epsilon given by this set. Also denote n a natural number and let the delta equal t divided by n, and consider the process delta x with piecewise constant trajectories given by the equation 3. And similarly, we consider the discrete valued grid process, delta x epsilon, with piecewise constant trajectories given for this equation, as well as the corresponding discrete time processes given for these equations. This corresponds, equation 6 says to, equations 5 and 6 to 3 and 4. This process is a discretization for X. Hence, the piecewise constant trajectories delta X is an approximation for process X. We assume that V bar is pointwise continuous in that this equality is true. There are one-to-one correspondence, say C, between the delta X epsilon and the discretization of X. So we can write this equation, and we define V bar D. The D is because, D here is because this is a discrete. This function depends of the discrete values of the trajectory of the process X, or more precisely of the discretization of X. So, hence we can write this limit of this form. This example here is for illustrate the equation 7 only. Approximating prices in discrete time and discrete state space for this value. The expectation, yes. For X given by the stochastic differential equation 1, we define these functions V n epsilon 1 and B n epsilon 2. We have these random variables are discrete here. And here the functions Q are given for these conditional expectations, where H, L, epsilon is this indicator function. Since X delta epsilon is discrete, we can write the function B n epsilon 1 of this form. This conditional this expectation conditional for conditional for Q, sorry. Conditional to this set is the correspond, because this is some discrete random variables. This is correspond to this conditional expectation where X here is continuous. Well, the next lemma is for simplify this expression, for example. This expression is this sum is very long, so this lemma, the recursion lemma, is for simplify this term. So if we define B n epsilon 1 n and B n epsilon 2 n for this function, that is this function here, in define and define this recursion where he is I and here and he is I minus 1. So if we go backward, we can recover the original B capital B functions, B1 and epsilon, and B2 and epsilon. So we have theorem 1, a sufficient condition for having this limit is having this limit, and whenever this limit is true, this term is the same function here with I minus 1. So this is the theorem that gives the desired result for us. Under assumption that we have this limit and this term is bounded, and that the implication of theorem 1 holds, we have that 2 is the price. This is this problem, or initial problem, rates of this form, where the Q functions are obtained for the Feynman-Cach formula. These PDEs here are simple because here the terminal conditions are indicator functions. The above method can be extended to Levy processes because, or since exists a Feynman-Cach formula for Levy process. So, the applications for pricing derivatives in stock markets or pricing interest rate derivatives is similar because with some modifications. For example, here, sorry. So, for example, in stock markets, we have an important characterization via the local volatility models postulated by Dupire, Professor Dupire, here. It's a pleasure for me. So this local volatility models is consistent with Feynman-Cach formula. So and so we can apply our method. So the expectation now is a price with this term here. So applying our method, we obtain the result for obtaining the price. It's similar with our method. The only difference is this factor. Similar for this case, for discrete case, this is when in this case the payoff is discrete, depend of some values of the trajectory of the process S. And in pricing derivatives, we know one factor model, short rate models are given for equation 28. And now the no arbitrage price of time zero and fixed income derivative is given by this expectation. Here, this is the new B bar. This is a expectation. For solve this expectation is similar, and so I can go quickly. The formula is the same with some modifications. So, the case of an interest rate Asian option, IDE. This is a Brazilian derivative and fixed income market. The realistic interbank deposit index, EDI, accumulates discretely according to this equation, 33. So we have the payoff and the discretization money market given by this equation. So we solve the EDI option numerically using the Basic model. For that, the parameters alpha, theta, sigma are these values here. The EDI starts with y0 for this value. The functions Q are obtained via Craig-Nicholson scheme. Since the example is with Basic, we provide analytically prices under the idealistic assumption of continuous updating of the EDI. We have here some results. The prices are given as a function of the observed value of the interest rate R0. Here, the dashed line is obtained by continuous updating of the EDI. In this case, exists a closed formula for that. And the other curves are obtained for our method. And here, the continuous line here is a blue continuous line, is obtained without use PDEs or without use the PDE, because in this case it's possible to obtain directly this price, these values, this price. So this is on these values for this figure. Here obtain is similar because here the similar dash line is the continuous update, and the other curve is solved using Craig-Nicholson method. Here for more days, and here we have other result here for 20 days using MATLAB. All the result was using MATLAB. The prices are here. Conclusions. We provide a new method for pricing path-dependent derivatives in stock and fixed income markets. The method deals with continuous time as well as discrete monitoring path-dependent derivatives on diffusion and on diffusions on Levy processes, consistent with the Feynman-Craig formula. The method is insensitive to the payoff format. The parallel computing is allowed. This is a counterpart for much time consumed in computation. In this case, in the case of the complete path-dependent derivatives with long lifetimes. It appears that the method presents good results and doesn't present instability in the range of low volatilities. This disadvantage often encountered in existing numerical methods. And some reference here. Thank you.
Questions?
The time discretization seems to be the normal one, and so the price discretization was with equally spaced levels, or I don't know. Can you go back?
Yeah. It's equally spaced. Yeah. Yes.
Yeah, and so I'm not sure I've understood the
yes.
transition mechanism. So
yeah. Discretization
Yeah.
of X. Yeah, this
Yeah,
is
yeah. So that's a double summation here. Yeah.
yes, equal spaces. Yeah.
Yes, and so how do you transition from? So basically, you have a grid, a rectangular grid,
Yes.
equally spaced in time,
Yes.
equally spaced in space.
Yes. Yes.
And so you have to define the transition mechanism, a bit like in a trinomial tree, for instance. I mean, yeah, that's the thing I have missed. So how do you transform the parameters of the dynamics, like the drift and the volatility, into probabilities of attaining different nodes in your scheme?
Here, this is a general. Here, sorry. Here is only discretization for X. In the discretization, no, how do you say? It's independent of this for these functions. It's in the discretization is independent for.
Okay.
This. Of what? If I understand correct, the question is it's questions about this function. Yes. Yes.
What kind of transition do you use? What kind of transition do you use to go from one step to the other? How do you do the transition? You discretize, and now you want to evolve in time X, because you're going to apply Feynman-Katz. So you want to solve the forward equation, the forward stochastic differential equation that you see there. How do you solve it? That's what we.
Yeah, I think I understand. Yeah, because I discretize the process X, but I come back for continuous case. I come back here for this problem on discretization, but in the final theorem we have this. Sorry. We have this approximation with this expectation that is continuous here. Here X is continuous. And here this is a expectation conditional to this set. These are discrete random variables. So it converge, this expectation converge to original expectation. Okay.
The link clear. You can go to the Feynman-Katz equation.
Feynman.
The Feynman. So the parameters actually appears in the Feynman-Katz. So the transition you have, because the expectation exactly the one step change from xi delta given xi minus 1 delta. So the Feynman-Katz gives you this expectation. And this expectation actually, we transform it to the conditional probabilities actually, if you have a discrete scenario framework. So you have a
I mean, if you got a node in your grid, so delta t after, so you're supposed to have a kind of a Gaussian distribution that you discretize with a finite number of points in space.
Yes.
I've not seen exactly how you transform the drift and the volatility into the probability scheme that tells you how likely it is to go to the next grid point. For instance, at one point in time, So how many levels at the next
Mhm.
step can you reach? In a trinomial tree, for instance, it would be
Uh-huh.
just 3 of them. Here, can it be bigger?
Yeah.
Step I have missed.
Okay.
But we can carry on after I answer this.
Mm. Let give me just 1 second to find because the step is in time is only one, always one step. So you go from one point to an arbitrary point in the grid, epsilon.
Mm-hmm.
No?
With which probability?
Exactly. This is the expectation. Vai lá para as fórmulas iniciais mesmo. No V1, V2. V1, V2. V1, V2. Né? V1, V2. Uhum. Ok. Não, vai para o V2 mesmo. V2, que tem o discreto. Tará. Não, vai aqui. Ok. Ok. The indicator function in the expectation inside the summation, you have Li and the Li plus epsilon.
Mm-hmm.
So you characterize this a grid space between Li and Li plus epsilon.
Mm-hmm.
So this is the point. See, the summation goes, you run in the Li.
Mm-hmm.
So you choose your Li, and so you indicate this point in the indicator function. Okay, so this means indicate the xi delta equal to a guy who is inside this interval. It's close in the left, so it's equal to Li. So this is actually the probability of x I delta being Li, given that xi minus 1 delta is equal to L. So here you have the transition. And the Feynman-Kac actually brings the discrete thing. We bring the discrete thing to the continuous, and the Feynman-Kac gives us the continuous to approximate this.
Okay, thank you.
We have one more question.
So, Bruno, the way I understand this, Juan, come back 1 slide, please. So if you see equation 10, the way I see it is like you have VD, this is the value over the path, the complete path, times the probability of that complete path, because each QI is the expectation of an indicator function. So you do like all the transition probabilities.
Thank you.
Okay, any more questions? So let's thank Juan again.
Thank you.